All right, so this is the beginning of Chapter 7. Chapter 7 is going to focus on exponential functions and how to transform them, and exponential equations. Some background that you should already have that will be useful in this chapter, so things you've learned along the way. A lot of this is grade 10, grade 9 stuff. But when you multiply powers with the same base, okay, x squared times x to the third, you write your base down again, and then you add the exponents. So 2 plus 3, x to the fifth. When you multiply powers with the same base again, all right, base is 2, write it down, add the exponents, 18 plus negative 3, 2 to the 15th. All right, this is going to be x to the 2 plus 1/2, adding fractions. So 2 over 1 becomes 4 over 2 plus 1 over 2. I'm getting a common denominator. So 4 over 2 plus 1 over 2 gives me x to the 5 over 2. So that's examples of how to multiply powers with the same base. You add the exponents. To divide powers with the same base, you write your base down again, then you subtract the exponents. So this will equal x squared. This will equal 8 minus negative 2. When you subtract a negative, it's like adding. 2 negatives make a positive, so I get b to the 10th. Okay, when you raise a power to a power, all right, you multiply the exponents. 5 times 2 gives me x to the 10th. Here it's y to the 8, all raised to the 1/2, so that'll become 8 times 1/2. Okay, half of 8 is 4. Or you could go top by top. 8 times 1 is 8, bottom by bottom. 1 times 2 is 2. 8 over 2 is 4. Okay, some other things that will help you in this unit when you're working with radicals. You should know what those look like as exponents. So if I want to turn a square root into an exponent, taking the square root of x is like raising x to the 1/2. Okay, so your index, that's the denominator. If there's nothing written here, it's understood to be the square root. So look where the 2 went in the denominator. And your exponent in under here, there's nothing written there, understood to be a 1. That goes as your numerator. So this became the denominator. I'll do it all the way around the back. So that 2 became the denominator. This exponent 1. Okay, so there's a 2 here and a 1 here. The cubed root, so that's x to the 1/3. Okay, you can see the denominator, or the index is 3, so that goes in the denominator. Index is 4. It's going to be 1 over 4. Here's an example where I've got an exponent underneath. So this would be x to the 2/5. Okay. The index always goes to the denominator. This would be x to the 6/7. Okay, just a couple of quick questions involving powers. 3 squared. 3 times, it doesn't mean 3 times 2, it means 3 times 3 is 9. 3 to the negative 2. Okay, 3 to the negative 2 means this. When you have a negative exponent, you take the reciprocal of the base. So the reciprocal of 3 is 1/3, and you make the exponent positive. And then I raise the numerator to the power of 2. 1 times 1 is 1. And I raise the denominator to the power of 2. 3 times 3 is 9. Okay, note the following. Okay, if 3 to the positive 2 is 9, 3 to the negative 2 is 1 over 9. If I have, I'll show you another example of that. Let's go 4 to the 3rd and 4 to the negative 3. 4 to the 3rd, it's not 12, it's 4 times 4 times 4. 4 times 4 is 16, times 4 is 64. Okay, so I get a 64 here. This one's going to equal the reciprocal of 64, which is 1 over 64. So a little shortcut you could do there. Instead of going 1/4 to the power of 3 and getting 1 over 64, If I know that 4 cubed is 64, a little shortcut is just 4 to the negative 3 would be 1 over 64. 2 to the 5th, all to the negative 3, that's going to equal 5 over 2 to the positive 3. 5 cubed, 125. 2 cubed, 8. All right, 2/5 to the positive 3 if I ask that question. I don't have to take the reciprocal of the base at all. I just go 2 cubed, 8. 5 cubed, 125. Note the difference. Negative 3, I get 125 over 8. Positive 3, I get 8 over 125 for reciprocals. Okay, and that'll help us in a few minutes when we start sketching or when we look at a couple of exponential functions. Some key ideas here in this unit. All right, an exponential function is of the form y equals c to the x, where c is greater than 0, and I'll add this. C cannot equal 1. C in this case just represents the base. Some textbooks use b to the x. The reason we're not using b in this is because we're talking b as our parameter that gives us our horizontal stretch factor. Okay, so it's kind of nice that they use c, but different texts will use different variables. It really doesn't matter. Okay, this point says, is increasing for c greater than 1. So if the base is greater than 1, you get an increasing function. Increasing functions look like this. As your x values get bigger, so as I work my way from left to right, look what's happening to my y values. They're getting bigger. Versus a decreasing function. If I work my way from left to right, so if I look at the left, my y values are high. As I move towards the right, the further right I move, the smaller my y values get. And in order for that to happen, my base has to be between 0 and 1. If your base is 1, okay, that's just 1 to the power of anything is just 1. That would just give you a horizontal line. That's why I said you won't see any with a base of 1. 1 to the first is 1, 1 to the second is 1, 1 to the third would be 1, 1 to the fourth would be 1. It would just make a horizontal line. Okay, so notice the base here. What's the base for an increasing function in this case? The base is 2, okay, greater than 1, increasing. In this case here, we're looking at the curve y equals 1/2 x. It's decreasing, so I get this shape. Okay, sometimes they call this growth. And we'll look at growth problems, and sometimes they call this decay. We'll look at decay problems. They have a domain, x belongs to the real numbers. All right, so without any transformations, this will be your domain. Okay. X belongs to the real numbers, or we could write it like this. From negative infinity to positive infinity. All right? That's what it would look like in interval notation. The range, okay, is y is greater than 0. Y belongs to the real numbers. Or we can write that as 0 to infinity, both in round brackets. Notice I put a round bracket in front of the 0 because it's greater than 0. Can't be equal to 0. Has a y-intercept of 1, so you could also write that as 0, 1. That's a point. Realize the difference between this and this. This is a point. That is an interval. That's an x value and another x value, where this is an x value and this is a y value. Has no y-intercept, sorry, no x-intercept, and has a horizontal asymptote of y equals 0. So the horizontal asymptote would be right on top of the x-axis for both of these curves. Both of those blue curves stay above that. The further right you go, the closer you're going to get to a height of 0, but you're never actually going to go through 0 or go into the negatives. Okay, so this information will stay the same for all the questions you're going to have to do for homework tonight. It'll change when we get into transforming them, but that'll be a couple videos down the road. So let's look at a couple of examples. It says graph each of the exponential functions, then identify the domain and range. So for both of these, the domain should be x belongs to the real numbers, and the range should be y is greater than 0 for both of them. Okay, one represents growth, one represents decay, or one is increasing, one is decreasing. Increasing because the base is greater than 1, decreasing because the base is between 0 and 1. Both of them should have no x-intercept. Both of them should have a y-intercept of 0, 1. And we can say increasing or decreasing, we already did that, and then the equation of the horizontal asymptote would be y equals 1. So let's just start with the first one. Okay? How would I graph this curve right here? Y equals 4 to the x. And this could be a base function in this unit. It's not like the last unit when we were talking y equals radical x and we were always transforming these points. Okay? It's going to depend on what this number is here. So this number could be a 4, could be a 2, could be a 5, could be a 1/2, could be a 2/3. It will change the y values here. The x values will always go from, we'll write -2 to +2, but the y values are going to change depending on what the base is. So x values, since x can be any x value at all, I can use a negative x value if I want. We'll just go from -2 to +2. Okay? I'm going to pull this up here, but we won't talk about it for a second. So 4, if I fill a 0 in for 4, let's start here. 4 to the power of 0. Well, anything to the power of 0 is not 0, it's actually 1. Okay? 4 to the power of 0, 3 to the power of 0, 1/2 to the power of 0, 10 to the power of 0, x to the power of 0, they all equal 1. This should be an easy calculation. If I fill that 1 in right here, 4 to the first, 4. If I fill a 2 in, 4 squared, that's 16. Okay, now knowing the shortcut I showed you on the previous 2 pages ago, or 2 pages prior to this, if I know that 4 to the first is 4, what's 4 to the -1? Well, it's the reciprocal of 4. 4 squared is 16, 4 to the -2 is the reciprocal of 16, or 1/16, and here's why, okay? Here's where this value comes from. When I go 4 to the -2, remember the rule I just showed you, when you have a negative exponent, you take the reciprocal of the base. So only if the exponent is negative, okay? Take the reciprocal of the base, and when you do that, the exponent becomes positive. And then 1/4 squared is 1/16. Okay? 4 to the -1 becomes 1/4 to the first, which is 1/4. So those are my points. And here's how we plot them. Okay? -2, 1/16. That would be 2 to the left, and look, it's up a 1/16 of a block. Okay, it's just above the x-axis. -1, 1/4, that's -1 to the left, or 1 to the left, and up 1/4 of a block, or 0.25. 0, 1, that means don't go left or right, just go up 1. 1 right, up 4, so 1 right, up 4, and then 2 right, up 16. So right 2, up 16. And I join those with a smooth curve, and notice there's an arrow on both ends, and that is because the domain can be any x value at all, from -infinity to +infinity, where x belongs to the real numbers. Let's use the curve to help us answer this question. The domain and range, so the domain will be x such that x belongs to the real numbers, or -infinity to to positive infinity. Okay, there's an arrow pointing left, so it's going towards negative infinity. There's an arrow going up and to the right, so it's going towards positive infinity. Okay, there's my domain. The range is y such that y is greater than 0. Y belongs to the real numbers. Check this out. If I were to slide up the, let's take a horizontal line. If I were to slide that line up the y-axis, when do I hit the curve? Boom, right there. That's when I hit the blue curve. Now remember, it's never going to go through the x-axis. It's never actually going to attain a height of 0. Okay, because it's always going to be like 1 over 32, 1 over 64, 1 over 128. So the bigger the denominator gets, the closer it's going to get to 0, but it'll never go through the x-axis. So that is why we see the just greater than 0 and not greater than or equal to. In interval notation, that would go from 0 to infinity. So the domain and range are done. Okay. The x and y intercept. So we can look at the graph. The x-intercept. Where does this blue curve cross the x-axis? Well, we just got done saying it doesn't. Okay, it doesn't go through the x-axis. We don't get negative y values. So for the x-intercept, we'll say there is none or it's not applicable. For the y-intercept, where does this curve cross the y-axis? That's right here. Here's the y-axis. The blue curve touches a height of 1. So you can say 0, 1 or y equals 1, same thing. It wants to know whether the graph represents increasing or decreasing. In this case, it's increasing. As my x values get bigger, as I move to the right, my y values are also getting bigger. That's why it's increasing. Or we could say the base is equal to, not b, but c is equal to 4 in this case. So it's greater than 1. We knew it was going to be increasing. And finally, where's the equation of the horizontal asymptote? The horizontal asymptote is at y equals 0. That is this x-axis, this green line right here. Let me slide that up. Okay, that line right there, that dashed green line, has a equation of y equals 0. Okay, I'm going to copy all of this. New full screen. I'm going to clone it. I'm going to send it down here because that information is going to be the same with the exception of one word. Okay, so we'll talk about it in a second. But for part B, we are looking at the equation y equals, or is it f of x equals? Yeah, f of x equals 1/2 x. Same thing, f of x is just the y value, it's the function's height. In this case, the base is 1/2. Okay, so if the base is 1/2, we know it's between 0 and 1. If my c value is 1/2, that would change this word from increasing to decreasing. Okay, why? Check it out. Decreasing if the base is between 0 and 1. 0.5 or 1 over 2 would fit right in there. It's greater than 0, less than 1. The first curve, part A, was increasing because 4 is greater than 1. That means it's increasing. Let's make a little table and graph these. So remember, that just means y equals 1/2 to the power of x. Again, I can use, in this unit, you can use any x values you like. I'll go from -2 to +2, so that, remember when we get into transforming them, these are the x values you're going to transform. The y values are dependent on what your base is, right? The y is the dependent variable, x is the independent variable. So, again, I like to start in the middle somewhere. I start here at 0. 1/2 to the 0, anything to the power of 0 is 1. 1/2 to the power of 1, that's 1 to the first, 1, 2 to the first, 2. So 1/2 to the first is 1/2. 1/2 squared, if I square 1, it's not 1 times 2, it's 1 times itself, 1. That would give me a 1. 2 times itself, 2 squared is 4. Now remember, if 1/2 to the first is 1/2, 1/2 to the -1 would be the reciprocal of this, 2. 1/2 to the -2 would be the reciprocal of this, 4. Just so you know why, show that again, 1/2 to the -2. If you can't do these little shortcuts, all right, hopefully they'll stick a little, or once you get working with these, but 1/2 to the -2, you take the reciprocal of the base. The reciprocal of 1 over 2 is 2 over 1, or just 2. Make the exponent positive. That's how I get a 4. 2 squared is 4. All right, and then I plot these points. Look at these ones. They start high, so here's -2, 4. Here's -1, 2. 0, 1. 1 to the right, up a half a block. 2 to the right, up a quarter of a block. 3 to the left, up 8. That's if you put a -3 in. You'd get 8. That's 2, 1/2 to the -3 is like 2 to the third. 2 to the third is 8. Okay, and I join them with a smooth curve. Notice there's an arrow here, and once again you can see all of this information is the same. The domain x belongs to the real numbers. The range y is greater than 0. This blue curve is all above the x-axis. The further right you move, the closer you're going to get to the x-axis, but you're never going to go below it. So that tells us that there's no x-intercept. The y-intercept is 0, 1, or y equals 1. Check it out. Here's the y-axis. There's where the blue curve crosses it. That's the point 0, 1. We said it's decreasing because the base was between 0 and 1, and we know that the horizontal asymptote is this line right here, y equals 0, the x-axis. Now, that doesn't mean there will never be an x-intercept, but in order to get an x-intercept, we'd have to apply some sort of transformation. Easiest way to do it would be to just shift this curve down. If you move all these points down, you apply a vertical translation, then you could make that happen. Okay, it would go through the x-axis. Think of this curve going like that. Well, there it goes through the x-axis right there. But we're not going to transform them today. That's a lesson for the next video. One last question to look at. How would you come up with an equation for this curve? Well, first of all, ask yourself this. Is it increasing or decreasing? How do you tell? Well, as I move from left to right, do my y values get bigger or smaller? The answer is smaller. That means it's decreasing. That means that my c value is greater than 0, but less than 1. So the goal is to try and figure out c in this case. So I want to write an equation of the form y equals c to the x. In order to do that, I need to look for a pattern in the points. So here's the point, -2, 16, -1, 4, 0, 1. So as my x values get bigger, my y values are getting smaller. You might ask yourself, what's happening to these? And a lot of people say, well, you divide by 4. That's true, but dividing by 4 is the same as multiplying by 1/4. Okay? And that's what we got to use here. We got to use this number, the 1/4. So my equation should be y equals 1/4 to the power of x. And to prove if that's correct, I could use either this point or this point, fill in my x value, fill in a -2, and I should get 16 for my y value. Fill in a -1, and I should get 4 for my y value. Why is it no good to use this point? You shouldn't use this one, because it wouldn't matter what the base is. Even if I got this wrong, any base raised to the power of 0 is 1. So use something other than 0, 1. All right, so let's just try this. If I go y equals 1/4, let's try and fill in the -2. So -2 is my input. Y equals 4/1. Sorry, 1/4 would become 4/1, and that exponent -2 would become a +2. That would leave me with y equals 16. So when x is -2, you can see y equals 16. That means that this equation is correct. Now, what you can do is you can try these questions on page 343, number 1 to 8.